So we're going to continue our lesson with earthquakes. So let's reflect and review something that we already talked about. We talked about the different types of folds. Folds was a vocabulary word, but folds was rocks bending into a series of waves. Now, one thing I want you to see is that we have an anticline. See how it kind of goes up? Then we have a syncline. And sync basically, if someone says they sync in something, I think of like downloading. So it went down. Um, usually, we upload, I guess, like antiviruses and stuff to computers. So anti, we upload, sync, we download. Monocline is basically like steps. Okay. Harris is three, this upward, downward, and again like steps. So anticlines are the most common form by the upfolding or going up a hill. Synclines basically make basins. Monoclines is like again steps. So what is a fault? Now we did talk about what a fault was before, but now we're going to make sure we understand what is the purpose of a fault and what a fault can actually do. So a break in the lithosphere. Again, we live where on the lithosphere on the Earth's crust. Um, most earthquakes occur in this way. So this is what happens when we have friction between plates that prevent them from moving. So strain builds up. So if you ever like not move your leg for a little bit, and as soon as you move it, you hear like a big old pop, or it like has this grinding sound, or it's hard to move. All of that right there is basically like what an earthquake is. So rock deforms. Eventually, the strain becomes great enough that the rock moves and returns to normal shape. But this is caused by, again, this causes an earthquake, and it's called an elastic rebound theory. You ever get up and your knee maybe like popped or something, but you're like, man, it felt good, but it kind of made you shake a little bit. Well, elastic rebound theory. So faults are formed by fractures in rocks. So whenever you have like a broken leg or you hurt something, it becomes what we consider a fracture. But what happens is everything shifts if it's broken. So we have a hanging wall. We have to identify these pieces. So the hanging wall, as you see here, hangs over the foot wall. Well, the foot wall is going to be below the fault line, and you see it's obviously near the bottom or below. So what is normal? Well, normal is when the hanging wall moves down relative to the foot wall block. So as you see here, here was the fault line at the end of the lithosphere. So the hanging wall, this is normal, it moved down. Now, what is reverse? Well, this is where the ground, the hanging wall goes up above the foot wall. Usually when you see earthquakes, you see the earth split or the earth kind of pieces fall down. That's normal. You don't you're not usually seeing the earth pop back up, but that's called the reverse. Then we have thrust. Thrust is what reverse fault happens with dips of less than 45 degrees. Okay, as you see, it's also a change. It's not just going up and down. It was like a little shift. And again, strike slip is when they move horizontal. So it just kind of slides against each other. So this is where maybe a road right here, and all of a sudden now the road's here because the earth broke it and kind of shifted it up a little bit. Now tell me, what is an earthquake? Obviously, when the earth quakes, right? So when the earth is moving or shaking, so the shaking of the earth's crust by a release of energy. So earthquakes can be caused by if a volcano erupts. It can be caused if a cavern, you've seen the caverns that are underground, and they fall. Uh, a meteor comes flying down and hits Earth, then an earthquake can happen. A strain built up along boundaries. So just again, like if you just been sitting down for so long, and when you get up, you have the popping noises that occurs. That's kind of what happens. Now, we live here by, military base. I would never be surprised if an earthquake came here, especially if we keep dropping bombs and bombs and bombs. Eventually, the impact can cause a mini earthquake. Now, there's three parts of earthquake you have to know. You have to understand the focus, the epicenter, and the fault. So the focus is where the point right here, where the earthquake starts. So this is where it starts at. The epicenter, because are we in the middle of the earth? No, we don't know where the lithosphere it actually starts, but we do know where it hits at the epicenter. So the epicenter is located directly above where it happens underground. Now the fault line is basically associated where the movement of the lithosphere plates have occurred. So that's right here. It moved. And so now as it moved, the epicenter is here. Now let's go back to the elastic rebound hypothesis. Well, the thing is, it's called release of built up energy. Yes, these are real pictures of an earthquake and what could basically take place. Um, Most earthquakes are produced by rapid release of elastic energy stored in rock that has been subjected to great forces. Look at this. Shook a little bit, everything just kind of collapsed. So now you can see the hanging and the foot. When the strength of the rock is exceeded, it breaks and causes a vibration of the earthquake. So the rock is exceeded, it breaks and causing a earthquake. Now, what is a foreshock versus an aftershock? So a foreshock is a small quake that becomes before a major earthquake. So a foreshock is like, okay, we got a little tremble. Like, you ever feel that when you go on a roller coaster and they give you that little dip and then they go back up, and then you got that big dip? Well, that's what happens for the foreshock and aftershock. So you always have to be anticipating right before you have a big major dip. Well, we have a huge foreshock, a small one that kind of gets you ready for it. An aftershock is where it's another small quake. So roller coasters be like, we go up, go back up, That's pretty much it, and then it keeps on going that way. And that's one of the best ways to explain this. Now, how do we understand this though? How do we even know these earthquakes happen, and how do we even record this? Well, we could do it with seismology. Well, seismology is the study of earthquake waves. So this allows us to know how strong an earthquake is and where it hit at, where's the epicenter, where's the focus point. So the seismograph is basically what instrument that records the waves. And as you see here, I put a seismograph here, cartoon version, 3D version, and a real version. Seismographs are basically the record made on the seismograph. Now, there's two types of waves. We have P waves and we have S waves. Now, the S waves, we're going to first talk about the surface waves, though. So, surface waves are seismic waves. Seismic waves that travel along the outer layer. They move up, they move down, and they move side to side. Most destructive earthquake waves, okay? Most destructive. The last to arrive on the seismograph. So when we have the seismograph, you're gonna have like a little little place, and all of a sudden we got that big jump. So we got the foreshock and the aftershock. So here is the real shock. That is very important. Now we can, if you look at this chart, you can see where it says the first P wave. So between each one of these lines is 1 minute. So this is the body wave, as you see, and then we have the surface waves. Now, we can say how long did it take from the first sign until the surface waves develop. So 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, we started seeing things, right? 6, 7. So we know within between 5 and 7 minutes, that's when the earthquake happened. Now, how long did the earthquake last? Well, 1, 2, 3, about 2 to 3 minutes. All right, so the best way you can understand these is, as we know, is P waves. Now, P waves is what they call push, compress, and then we have pull, expand. And so I tried to give you an idea that basically like a slinky. You know, when you pull it in one direction, these are also known as compressional waves. These can travel through solid, liquid, and gas. This is, though, the fastest waves. Now, S waves shakes at right angles in the direction. So if you had a rope and you did the rope, you will see the rope kind of make a little spiral. These are also known as transverse waves. So here is the key point. Compression, and this is push and pull in the direction that the wave travels. And of course, S waves is at right angles to the direction of travel. P waves is known as compression waves. S waves is known as transverse waves. Now, this one can travel through solid, liquid, gas. This one can only travel through solids. P waves are faster. S waves are slower, but faster than surface waves. So our primary waves, so again, P waves, we call them push and pull, travel through solid, liquids, gas, and this is the fastest. Now, how can we identify the wavelength? Wavelength is from one compression to the next. So here's one compression, here's the next compression. Refraction is the area in between. So as you see, that is one wavelength. So when it's real tight together. Surface waves, just to review it, travel on the Earth's surface. P waves, there are two types. We have long waves and we have Rayleigh waves. These again causes a lot of damage for surface waves. Okay. Now we're gonna actually learn how to locate an earthquake by using this chart. And the reason why is because this is on your test at the end of the school year. Now, there is a difference in P wave and S wave velocities, especially where it locates on the epicenter. Now we're going to use a travel time graph, and we need at least 3 seismograph station data, but we're going to practice over time. So again, locating earthquakes. P waves and S waves travel at different speeds. Their difference in their arrival. Times can be used to determine the distance away from the earthquakes occurred. So here you're going to see that the P waves and you have the S waves. So remember the compressions levels tell you your wavelength. Now this right here is measuring your wavelength. And so we take S minus P, will give us how long it was, and we have a little ruler to identify it. So the intensity and magnitude of earthquakes, we have two different types of measurements. So we measure by intensity and magnitude. Well, what is the difference? Well, intensity is the measure amount of the earthquake shaken at a given location and based on the amount of damage. Okay? Magnitude is the size of the seismic waves that the energy is released. So when we say, hey, this intensity was a level 5, that means the shaking was moderate and the damage was very light. But if we look here at this place and I say, hey, look here. Well, when you count it up, we realize that's like a level 10. That was violent and very, very destructive. But then if I look here where it's barely even blue or purple right here, that is weak. It was intensity of level 2, which means it was weak, but the magnitude of the energy wasn't as strong, so it didn't really cause no damage. Now, what's the scale that we use for this? It's called the Richter scale. The Richter scale basically lets us know if it's 1, 2, 3, 4, so insignificant to extraordinary. Based on it, like we just had an earthquake here in North Carolina. I think we're averaged around 5 point something or 6. So we're about right here. That is actually in the middle. So we're actually at a place that, hey, whoa, that's getting major. What happened to hit a 9? Um, Tenfold system is what it is. The amount of shaking for a 5.0 earthquake is 10 times greater than the shaking produced of a 4. So everything is times 10. So the moment magnitude, more precise measuring of earthquakes. Now, you can calculate this with several factors: the average amount of movement around the fault, the area that broke, the strength of the broken rock. So most widely used, so we use a Richter scale and the moment magnitude. Now that's Richter scale tells us the intensity. Now how do we get the magnitude? We use the moment magnitude. And as you see here, this was our most heaviest one and it kind of went there. So it does spread. Now there has been different destructions from the earthquake. So we have seismic vibration, damage to buildings. So we also have the intensity, duration, nature of the material, design of the structure. Liquefaction is stable a soil that turns into liquid that is able not to support structures anymore. So some things, as you look, it can get real sunken in. Sometimes it just kind of breaks the ground. Now you have to be able to identify these on a worksheet. So because P waves and S waves travel at different speeds, we can actually use a difference in their arrival times at the given location to figure out the distance of the earthquake's epicenter. This information is again what we talked about earlier, the travel time graph. As you see here, what is the difference between the S wave and P wave when it came? Because these are the compressions. So when you estimate these are times here, you go up and down. These blocks equal about 5 minutes apart. Reading the time graph. So time in minutes is for the arrival of the waves. All right. Distance from the recording station is here. And that's always at the bottom. X and Y. The time when a wave will be received when given the distance between the seismic station and epicenter. So what we're going to do is find the distance along the x-axis. Make sure you're using the correct units. So follow the distance where the S wave or P waves curve. Uh, go across to the y-axis to find the time. So when will the P wave, we say it here, earthquake epicenter is approximately 3,000 kilometers from the seismic station? Well, again, we find the distance in the x-axis, and it said 3,000. And then from there, it says follow the distance line up to where it meets which wave is talking about. So it says the P wave. So we go all the way up, and we stop here. Now, when we stop here, we have to see about how long that would be. I know my lines are not going to be straight, but give or take, let's just say 8.3 minutes. That's how long it would take. Okay, any questions with that? If so, please send me an email. Now we need to find the distance between the seismic station and epicenter from the given arrival time. So here we have to get the time from the y-axis, follow the time until you hit the wave curve line, go up or down, and that's how we go our distance. So if the first S wave, so here's our S wave right here, arrives after 9 minutes, so 9 minutes. What is the distance between the epicenter and the seismic station? So this is where I hit. My distance is 1,500 miles. To find the distance between the seismic station and the epicenter, given the difference in arrivals of S waves and P waves, first we must look at the S wave curve and the P wave curve to find where they are separated. Follow that line up or down into the approximate units. Example, the difference in P waves estimate time is 5 minutes. How far is the seismic station from the epicenter in miles? So what would the difference in travel times between the first P wave and the S wave at 1500? So here's 1500. So between S and P. So here's S and P. Right? So we got to figure out what's the time difference in between. Well, if every block is a minute, so 1, 2, 3, 4. The difference in that will be about 4 minutes. Now we need to find the difference in wave arrival time, given the distance between the seismic station and the epicenter. So follow the distance around the x-axis. Follow the distance line to the P wave and S wave curves. Using the times on the y-axis, calculate the difference arrivals of the two waves. Okay. So what would the difference be in travel if the P wave in the first wave, if the seismic station is 4,000 kilometers from the epicenter? All right, so 4,000 kilometers. Okay, and I want to say that's about. Here is the times for these. So that's about 12.5, and this is 7. And so you are supposed to follow the line up to the P wave and S wave curves. Using the times on the y-axis, calculate the difference in the arrivals of the two times. So 2.5 minus 7 is 5.5. That is the difference of the times.